Several days ago, Donald Trump greenlighted the export of Nvidia's H200 AI chips to China with a 25% cut from the sales, which raised concerns about America's national security and the possibility of yielding the country's technological edge to China. Some exclaimed for the lift of the export control as a victory for the Chinese chip industry, but in reality, it may delay China's own tech development. The U.S. still prohibits ASML from selling DUV and EUV machines to China, hoping to slow down China's progress in the chip industry. The rivalry between the two largest economies has never changed. Hi everyone, welcome back to Difference Frames the World, a channel to review global events through a different lens. Today we discuss China's chip industry at the lithography frontier, about its progress, constraints, and the long road to semiconductor independence. In the modern world, semiconductors are no longer just industrial inputs, they are strategic infrastructure. From artificial intelligence and cloud computing to telecommunications, automobiles, and military systems, advanced chips determine economic competitiveness and national power. Control over semiconductor manufacturing capacity, especially at the leading edge, has therefore become one of the defining strategic issues of the 21st century. China's semiconductor ambitions must be understood within this broader context. For decades, China has been not only the world's largest consumer of chips, but also one of the weakest producers of advanced logic semiconductors. This imbalance has left the country exposed to external pressure, a vulnerability that became increasingly evident as geopolitical tensions intensified and export controls tightened. Against this backdrop, the recent confirmation that Semiconductor Manufacturing International Corporation, SMIC, has achieved volume production of a 5nm class process node, known internally as SMIC N+3, represents a watershed moment. Even more striking is that this achievement was realized without access to extreme ultraviolet, EUV, lithography, the technology considered essential for advanced semiconductor manufacturing. Yet this breakthrough, while impressive, also exposes the limits of China's current approach and the enormous technical and economic challenges that remain. SMIC's N+3 node is officially the most advanced semiconductor manufacturing process currently in production in China. Analysis of Huawei's Kirin 9030 has confirmed that the chip was manufactured using this node, placing it a full generation ahead of SMIC's earlier N+2 process, which is considered a 7nm class node. The importance of this achievement cannot be overstated. For years, industry consensus held that producing 5nm class logic chips without EUV lithography was either economically impractical or outright impossible at scale. SMIC's success demonstrates that, under sufficient pressure, and with enough engineering ingenuity, the boundaries of what is technically possible can be pushed further than previously assumed. However, this achievement is best understood as a triumph of engineering under constraint rather than a replacement for EUV-based manufacturing. Lithography is the heart of semiconductor manufacturing. It is the process by which patterns are transferred onto silicon wafers using light. The smaller the wavelength of that light, the finer the patterns that can be printed. Modern EUV lithography uses light with a wavelength of 13.5 nanometers, allowing chipmakers to print extremely small features with relatively few processing steps. By contrast, deep ultraviolet DUV lithography, even in its most advanced immersion form, uses a 193 nanometer wavelength. Under normal circumstances, DUV lithography is insufficient for 5nm class nodes. However, SMIC has relied on aggressive multi-patterning techniques, including variants of self-aligned quadruple patterning, SAQP, to compensate for the wavelength limitation. In simple terms, multi-patterning involves printing the same layer multiple times, each time slightly offset, and then etching away material in stages to achieve finer features. While this approach has been used for years in earlier process nodes, SMIC has pushed it to unprecedented levels. The result is a manufacturing flow that is far more complex than EUV-based processes. Each additional patterning step increases the risk of defects, alignment errors, and variability, making yield management extremely difficult. The central weakness of SMIC's N+3 node is not its technical feasibility, but its economic efficiency. Advanced semiconductor manufacturing is a game of yield. Even small reductions in yield can dramatically increase the cost per usable chip. In EUV-enabled fabs, the reduction in process steps allows for higher yields and lower defect density. In contrast, SMIC's DUV-based 5 nanometer class production requires many more steps, increasing both capital expenditure and operational costs. Reports indicate that SMIC faces significant yield challenges at N+3, particularly due to aggressively scaled metal pitches. As a result, a substantial portion of manufactured dies may be discarded or downgraded to lower performance products. It strongly suggests that chips like the Kirin 9030 are being produced at a higher cost than they should have been with EUV machines, and the profitability is sacrificed in favor of strategic objectives. In effect, SMIC is trading economics for sovereignty. This trade-off may be acceptable, even necessary, in a geopolitical context, but it underscores why EUV remains so central to the global semiconductor hierarchy. Extreme ultraviolet lithography is the single most critical choke point in advanced semiconductor manufacturing. EUV machines are not just incremental improvements over DUV tools, they represent a fundamental shift in how advanced chips are made. Each EUV system is a marvel of engineering. It requires a plasma light source generated by firing high-powered lasers at tin droplets, ultra-precise mirrors polished to atomic smoothness, and vacuum systems operating at extraordinary tolerances. No other company besides ASML has been able to integrate these components into a commercially viable product at present, even though reports say Huawei is testing China's own EUV machine in its Dongguan plant. For leading chip makers, EUV is not optional. It enables fewer process steps, higher yields, lower power consumption, and faster time to market. Without it, producing competitive chips at 5 nanometers and below becomes exponentially harder. China's inability to access EUV machines, therefore, represents a structural limitation rather than a temporary inconvenience. The Netherlands occupies a uniquely influential position in the semiconductor supply chain because ASML is based there. Although ASML is a private company, its products fall under national export control regimes, which are shaped by both domestic policy and alliance considerations. Since 2019, the export of EUV lithography systems to China has been effectively blocked. No Chinese foundry has ever received an EUV machine, despite placing orders many years earlier. In recent years, these restrictions have expanded to include increasingly advanced DUV immersion systems, particularly those capable of supporting nodes below 10 nanometers. Under updated export control frameworks, even some mid-range DUV machines now require special licenses before being shipped to China. The approval process has become more restrictive, slower, and more politically sensitive. These controls reflect a broader shift in Western policy. Advanced semiconductor manufacturing equipment is now treated not merely as commercial technology, but as a strategic asset. While the EUV ban attracts the most attention, restrictions on DUV equipment may prove just as consequential in the long run. DUV immersion scanners remain essential not only for advanced nodes but also for mature processes used in automotive chips, power management ICs, and industrial electronics. By limiting China's access to the most capable DUV tools, export controls increase costs, reduce flexibility, and constrain capacity expansion across the entire semiconductor ecosystem. For SMIC, continued reliance on older ASML DUV tools, some based on designs from the last century, imposes additional engineering challenges. These machines can be optimized and pushed beyond their original specifications, but only up to a point. The tightening of DUV exports therefore reinforces the strategic nature of China's predicament. Even maintaining current capabilities becomes more difficult over time. Although China now has its own DUV machines, they are reliable for the production of 28 nanometer or higher chips, so they cannot match high-end DUV scanners from ASML, which can produce chips under 10 nanometers. Faced with external restrictions, China has invested heavily in developing domestic lithography equipment. Companies such as Shanghai Yuliangsheng Technology and SME have made progress in developing DUV scanners suitable for legacy and mid-range nodes, which meet 60% of the global needs. These machines are important, but they are not substitutes for ASML's most advanced systems. Reports of SMIC testing domestically developed immersion DUV tools should be seen as part of a long-term capacity-building effort rather than a breakthrough. Developing competitive lithography equipment requires not only optical expertise, but also decades of accumulated know-how in materials science, precision engineering, software, and supply chain coordination. ASML's dominance is the product of a global ecosystem that cannot be replicated quickly. While there is speculation that China has developed prototype EUV systems, they still face extraordinary technical hurdles. Even if a domestic EUV machine were truly demonstrated, achieving the reliability, throughput, and yield required for high-volume manufacturing would likely take many additional years. China's semiconductor strategy is defined by persistence. Massive state funding, coordinated industrial policy, and political prioritization ensure that progress continues even when returns are uncertain. SMIC's N+3 node exemplifies this approach. It is not the most efficient way to make 5nm class chips, but it proves that China cannot be completely shut out of advanced chip manufacturing. At the same time, this progress does not eliminate the technology gap. Leading foundries such as TSMC and Samsung continue to advance toward 3nm and beyond, leveraging EUV and preparing for next-generation high-NA EUV tools. Each generational leap increases the complexity and cost of catching up. The result is a semiconductor landscape defined not by absolute exclusion, but by asymmetric capability. The struggle over lithography technology has broader consequences for the global semiconductor industry. Export controls and national security considerations are driving fragmentation, redundancy, and duplication of effort. China's chip industry is building parallel supply chains that are less efficient but more resilient to external pressure. Western countries, in turn, are investing heavily in domestic manufacturing capacity to reduce dependence on Asian fabs. This fragmentation increases costs, slows innovation, and undermines the economies of scale that once defined the semiconductor industry. Yet from a strategic perspective, governments appear willing to accept these inefficiencies. China's chip industry has reached a critical milestone. SMIC's ability to produce 5nm class chips without EUV lithography demonstrates extraordinary engineering determination and strategic resolve. It shows that technological choke points can delay progress, but they do not guarantee stagnation. At the same time, the limitations of this approach are clear. Without access to EUV and the most advanced DUV tools, China's semiconductor industry faces persistent challenges in yield, cost, and scalability. Export controls from the Netherlands and other Western countries remain a defining constraint, shaping not only China's industrial trajectory but the future of the global semiconductor ecosystem. In the end, China's semiconductor story is not one of sudden breakthrough or inevitable failure. It is a story of incremental progress under pressure, where engineering ingenuity collides with geopolitical reality. China is looking to invest up to $70 billion more to speed up the growth of its semiconductor industry. This funding would add to existing efforts to improve chip design and manufacturing, trying to catch up with leaders like Nvidia, even as U.S. rules on advanced graphics cards change. In the past year, Beijing has launched numerous projects to boost chip production, reduce reliance on U.S. technology, and address shortages. While these actions have increased local production and limited the use of foreign hardware, China's chip designs still lag behind Nvidia's and AMD's by several generations. A large new investment could help close this gap. While the exact amount and recipients are still being decided, estimates range from $28 billion to $70 billion. If it reaches the higher figure, it would surpass the U.S. CHIPS Act funding and become the largest government-led semiconductor investment in the world. Who will win the chip war in the end, China or the U.S.? Please post your answers below for other viewers to consider.